One of the simplest classification algorithms is what's called the k-nearest neighbor algorithm. Sometimes we abbreviate by KNN. And so remember, for the classification problem, we have some sequence, some data, x1, y1 to xn, yn, where each of the x's is some point. Let's say, for now, let's say they're in Rd, d-dimensional real space. And the y's are, for classification, they're in some finite set. So for now, let's think about the case of binary classification when the y's take only two possible values. And then, so we're given these points, these data, and then we're given a new x, and we have to classify what is the y corresponding to that x. So let's so let me tell you the main idea, the big picture. What the k-nearest neighbor algorithm does is it takes this new point and it classifies it according to a majority vote of the k-nearest points in the data set. Sometimes we call this the training data. So it's a majority vote of the k-nearest points. So neighbor is sort of a funny, not exactly the right way to say this. It's the k-nearest points might be a better way to describe it. So let me illustrate this with just an example here. So say we've got these points in, let's suppose that d is 2. So this is R2. So this is, the plane. And maybe I've got some points. Let's draw the ones in red. So, what happened to my red? Oh, there's my red. Okay. So maybe we've got some ones here. And I'll draw in blue the zeros. And we've got some zeros. Maybe something like that. That's good. Now, so each of these is a point in R2. So each of these points is an x, and the y, so the label is the corresponding y for that point. Now we're given a new point. Let's say maybe this point here. This is our new x, and we have to classify it. Well, let's take first the case of k equals 1. Now, so I should say there's some, in the k-nearest neighbor algorithm, we're assuming some distance metric. So there's some metric, dx x prime, so where x and x prime are, these are points in, so x and x prime are points in Rd. And this is some distance metric, or maybe more generally just some measure of dissimilarity between these 2 points. And for now, just to keep things nice and simple, we'll take this to be the Euclidean distance. So this is so let's see, if we square it, then the formula is a little bit simpler. Sum from as I goes from 1 to d of the coordinates. So to make the connection with this, let me denote these using their. So this is xi and xj. xi, xj, xi to xj for consistency here, and then that's sum over k. So that's ik, jk, sum of the squares. So it's the sum of the squares of the individual components. So here I'm writing xi, for example, that's xi, to be just xi1, xi2, and so on up to xid. Just to make this consistent with our previous notation. So let's take this Euclidean distance as our, so I squared this so I wouldn't have to take the square root. So let's take this just for now, we'll take the Euclidean distance, and let's think about the case of k equals 1. So we got this point here, this is our new x, and the nearest point looks like probably this one here. So we would classify this as a 1. So the k nearest neighbor algorithm for k equals 1, classify this point as a 1. Now maybe if we had another point, say over here, and it looks like this one's closest, so we would classify that as a 0. On the other hand, so let's consider a little more generally, say for k equals 3. So for k equals 3, let's look at this one. We're going to find the 3 nearest points in our data set, and it looks like probably these 3. So another way to say that is you would take the ball around, centered at that point, try to make that a circular ball there. Take the ball centered around that point, the smallest such ball that contains three or more points. Sometimes there could be ties. So let's say we take the smallest ball that contains at least 3 points. Or there might not be exactly the smallest ball. We'll make it the smallest closed ball, say, just to be topologically precise. But you don't need to worry too much about that if you don't know topology. So take the smallest closed ball that contains 3 points, 3 or more points, and then now, since we're taking the, as I said, the majority vote of the k nearest points, that's what k nearest neighbor does, then in this case, that would just be, we would classify this as a 1. And for this guy, looks like these are probably the 3 nearest. So, so this probably this ball looks something like this. Oh, my bad drawing skills here. But you can see that then we would classify that as a 0. So that's the k nearest neighbor algorithm. Very, very simple algorithm, very easy to understand. And this is a classic, very classic sort of machine learning algorithm. And it often works, it can work fairly well. Has some theoretical guarantees. In the limit as n gets very large, there are some theoretical guarantees about the performance of the k nearest neighbor algorithm. I'm not going to make precise. And also, so the k nearest neighbor algorithm has a probabilistic formulation, which we can describe in the following way. So we can define a probability. So let's say, get rid of this, distracted. So let's say, okay, for this data and a new point x, we'll define a random variable y. So let's say this is our x here. So we'll define a random variable y with the following. So this is a probabilistic interpretation. Probabilistic interpretation. Define a random variable y with PMF p, where p of a value little y equals it equals the fraction of points. So we'll fix k. So we fix our data, we fix some point, fix k, and this is the fraction of points. Let me call n k x to be these nearest points, these 3 nearest points in this case, when k is 3. Fraction of points in nkx with class, so fraction of points, say xi, such that yi, the corresponding y for that xi, takes the value y. So it's it's the fraction of points that for which these nearest neighbors take the value y. Their label is y. Their class is y. So here nkx is these are the k nearest points to x. So we're working with some for particular x. So this depends clearly on this data and on x. So to make that dependence precise, or to at least explicit, sometimes people write, even though it's not really a conditional probability, often in machine learning this is a very sort of standard thing that people do, is to write it as though it were a conditional probability. So they would write p of y given x and all these other values. Let's call these, let's call this d. So given y, or given x and d, we sometimes might write it this way, just to make that dependence explicit. It's not technically a conditional probability, since we haven't defined a joint distribution over all these things. And then you would classify, so you would predict. We use hat to denote an estimate or a prediction. So you would predict the value of y for which this fraction is maximized. So I'll just write it and then I'll explain what I mean. So for x, the label that you would predict is, so you take for each possible value, in this case y is just taking values 0 or 1. So for 0, you compute this thing, the fraction of points. And then for 1, you compute the fraction of points, and then you choose the value of y for which that was maximized. So this is exactly reproducing this majority vote, just putting it in a little bit of a probabilistic sort of framework. And this, going back to, so in another video I described the distinction between generative and discriminative models. And so this, since this model only defines a probability distribution that is the y's conditional on the x's, then this is a discriminative model, as opposed to generative, because we don't have any distribution for generating for generating the x's. We only have a way to conditionally to describe the distribution of y given x. So k nearest neighbor is discriminative. And let me briefly say, so how does one choose k? Well, this comes down to this suggests or points one in the direction of a very important problem, which is sort of how do you select the parameters for your model. And so k here is a parameter, and there are techniques for choosing the value of a parameter for your algorithm, such as cross-validation, and there's a whole area of what's called the bias variance trade-off, and the choice of this value of k relates to this. So in other videos we'll come back to those questions in more detail. So that's the k nearest neighbor algorithm.